Lesson 9.4 is on rotations and systems of quadratic equations. Our objectives are to rotate the coordinate axes to eliminate the xy term in equation of conics, to use the discriminant to classify conics, and to solve systems of quadratic equations. The first thing we're going to talk about is rotation of axes to eliminate an xy term. The general second degree equation, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 can be rewritten as a prime times x prime squared plus c prime times y prime squared plus d prime x prime plus e prime y prime plus f prime equals 0 by rotating the coordinate axes through an angle theta where cotangent to theta equals a minus c divided by b. The coefficients of the new equation are obtained by making the substitutions x equals x prime cosine theta minus y prime sine theta, and y equals x prime sine theta plus y prime cosine theta. The important thing is that as we work through, we have some formulas that are going to lead us. So the first one is cotangent to theta is equal to a minus c over b. Okay, that's the first formula that's going to be really helpful for us. Okay, this one right here. The second formula that's going to be really helpful for us is, so here's one, and then here, x is x prime and y is y prime. One of the things I like about this section is it puts together not all of, but a lot of the math that we've done this year. It goes back to using trig and the unit circle. We solve systems, we use algebra. So there's a lot that happens that makes it a nice culminating topic for the end of the year. So the first thing we're going to talk about is this equation. Write the equation xy plus 2 equals 0 in standard form and sketch its graph. So if you look at this equation, you immediately notice that there's no x squared term, there's no y squared term, so it doesn't even really seem to be a conic section. But what we can do is we can change it to make it one. And really, even though it doesn't look like an equation of a conic, it is because it has this xy term. So there's nothing in this equation here that says that any specific term has to be present. So because we have an xy, that fills this term right here, the bxy, and that's really all we need. So the first thing we're going to do is we're going to use cotangent to theta equals a minus c over b. Okay. In this equation, if we look up here, a goes with the x squared, which means a is 0. B goes with the xy term, so b is 1. And c goes with the y squared term, so c is 0. So cotangent of 2 theta equals 0 minus 0 over 1. That's 0. 0 minus 0 over 1, which means that cotangent to theta is equal to 0. Now, this is where our knowledge of the unit circle comes in, because in order to get the 2 theta isolated, we have to do inverse cotangent of 0. So remember, cotangent of 2 theta is really cosine of 2 theta over sine of 2 theta. By applying our unit circle knowledge, we figure out that 2 theta is equal to pi over 2. And then to finish isolating theta, we multiply by 1/2. So that means theta is pi over 4. Okay, so our angle of rotation is pi over 4. And this theta is going to be very helpful for the other formulas as we go through. So our angle of rotation is pi over 4. So what that means is that instead of being here, our xy axes where they normally are, they've been rotated pi over 4 radians, which is also 45 degrees. So that means that now they're going this way. Okay, they've been rotated. Okay, so everything's been rotated. Okay, so now we're going to continue using our formulas to figure out what x and y equal and what x prime and y prime equal. So the first thing we do is we set up x equals x prime cosine theta minus y prime sine theta, and y equals x prime sine theta plus y prime cosine theta. Okay, so that's the first thing we do. So from here, if we think back to our unit circle, if our theta is pi over 4, that means that sine and cosine are both root 2 over 2. Now, I know that we have done a lot with it in this form, root 2 over 2, but it's going to be easier to do the calculations if we actually unrationalize it, which sounds bizarre, but it'll make our life a little bit easier. So instead of using root 2 over 2, we're going to use cosine theta is equal to sine theta, because they're the same, and we're going to use 1 over root 2. Okay, there's less numbers, it's going to make everything easier. So when we go back over here and plug things into our formula, we get x equals x prime, cosine of theta is 1 over root 2, so times 1 over root 2, minus y prime, sine theta is also 1 over root 2. So simplifying this, we get x is equal to x prime over root 2 minus y prime over root 2. And then we can do the same thing for y. So y is equal to x prime times 1 over root 2 plus y prime times 1 over root 2. So y is x prime over root 2 plus y prime over root 2. Now you're probably wondering to yourself, like, why are we finding this? Why are we finding x and y in terms of x prime and y prime? Well, what we've done here is by introducing the sine and cosine, it's taking care of the rotation of everything. So what we do now is we take these newfound x and y values and we substitute them into the original equation here, the xy plus 2 equals 0. So instead of x, we're going to substitute in this here, x prime over root 2 minus y prime over root 2. And then we'll do the same thing for y. So x was x prime over root 2 minus y prime over root 2 times y, which is x prime over root 2 plus y prime over root 2. And then the rest of the equation was plus 2 equals 0. Luckily, in this case, we have conjugates. We have x prime over root 2 minus y prime over root 2 times x prime over root 2 plus y prime over 2. So they're conjugates. So we can use our shortcut for multiplying conjugates and do first times first. So when we do first times first, we'll get x prime squared over 2, because root 2 times root 2 is 2, minus y prime squared over 2, because root 2 times root 2 is 2. And then I have this plus 2, I can move it to the other side and make it minus 2. So now it's starting to look a lot more like what we're used to seeing with a conic section. We have a squared term and a fraction for x and a squared term and a fraction for y, and it equals a number on the other side. With the subtraction sign in between, it's telling us that this is probably going to be a hyperbola. To finish putting it in the form that a hyperbola would be, this here, this negative 2, has to be equal to 1. So I'm going to multiply both sides by negative 1/2. When I do so, I'm going to change the order of x prime and y prime because y prime is going to become positive, so I'm going to put that in front. So I get y prime squared over 4 minus x prime squared over 4 equals 1. So hey, look at that. Now it looks like a hyperbola. Okay, so now that we have our equation, we can determine that our center is located at 0, 0. I have vertices at 0, 2 and 0, negative 2. Now, here's where it's a little bit tricky, because these are the vertices on the rotated axes. Okay, so these are the location on the rotated axes. So remember, I sketched in the rotated axes. Now, if I could accurately measure where everything went, okay, so this was the x, and remember it rotated that way. So this is now x. and here was y, and so the y would have rotated that way. So this is now, that's our negative y. So here this would be our positive y. That would be negative x. If we were to graph these, I have the point 0, 2. So I would follow this new y-axis 2 units in the positive direction. And then I also have a point at 0, negative 2. So I would follow it 2 units on this negative y direction. But the problem comes in is we can estimate where 2 would be, but we don't really know where it would be. So what we have to do is we have to turn them back into points on the xy plane. Now, you're probably wondering, how do we do that? Well, we're just going to do more substitution. So we found these formulas right here. X equals x prime, y equals y prime. Ta-da! There's the formulas that are going to tell us where our new points are. So what we do is we take these equations and we substitute our 2 points into them to find our new equations. When we do that, see if I can fit it all on the screen. Probably not, but I'm going to try. Okay, so when we do that, we know that x equals, and to make my life a little bit easier, I'm going to rewrite this as just one fraction. They have a common denominator, so I can make it x prime minus y prime over root 2. And then y is equal to x prime plus y prime over root 2. So it's going to make substitution and simplifying a little bit easier. So now my first point I'm going to substitute in is the point 0, 2. Now, where it gets tricky is that I have to put it in for x and for y. So there's a lot of substituting going on here. So the first point, x prime is 0, y prime is negative 2 over root 2, y, x prime is 0 plus 2 over root 2. So now x is negative 2 over root 2, y is positive 2 over root 2. I can rationalize these. So when I do, I multiply by root 2, numerator, denominator. So I'll get x equals negative 2 root 2 over 2, y equals positive 2 root 2 over 2. So we can simplify the 2's. So we get the first ordered pair of negative root 2, positive root 2. Okay? You're like, gee, thanks, Ms. Brown. That's not much more accurate than our last problem. Okay. So now we have our first point, and we just repeat the process for the second point. So now our second x prime, y prime coordinate is 0, negative 2. So x would be equal to 0 plus 2 this time over root 2. Y would be equal to 0 minus 2 over root 2. All the math is exactly the same as it was before. The points have just been flip-flopped. So I'm going to jump down to just get root 2, negative root 2. Okay. So these are the ordered pairs for our vertices on the regular xy plane. So when I go back up to the graph and I look at that, I have, okay, now root 2 is approximately 1.4-ish, okay? So if I go over 1.4-ish and down 1.4-ish, oh look, I hit on that axis like I was supposed to. So I hit right about there, okay? And then I have another point, remember, if we go back down and look at it, I had another point at negative root 2, positive root 2. So this was positive root 2, negative root 2. Now I go negative root 2, positive root 2. Oh, look, I've got another one there. Okay? So remember, these are my vertices, and I'm not going to get too crazy with what these look like. Okay? I just want you to know that there's a vertice, and that it's a hyperbola, so it's going to come out like this, and my graphing on this is terrible. So if we switch over to the completed versions from a previous year and scroll down and look at the graph, okay, you can see that we've got the graph here. So these should have arrows, all right? Like I said, I'm not going to go crazy. I more care about that you know how to find all of these pieces algebraically, okay, and that you can plot them in relatively the correct area, and that you know that this is a hyperbola, not an ellipse or a parabola. So in terms of the graph, that doesn't, I want to see the axes here as you've rotated them. I want to see a general shape, but what I'm more interested in is all of this work through here. On to our next example. We are going to rotate the axes to eliminate the xy term in the equation 5x squared minus 2xy plus 5y squared minus 12 equals 0. So we are going to start by finding cotangent of 2 theta again. A is going to be 5, B is negative 2, C is 5. Remember, the formula is cotangent of 2 theta is equal to A minus C over B, which would be 5 minus 5 over negative 2, which gives us 0. Oh, look at that. It's exactly the same as last problem, okay? So that means that cotangent 2 theta equals 0, which means 2 theta is pi over 2, which means theta is pi over 4. Okay, it's the same math from the last example. Now we're going to use our equations for x and y to get our x prime and y prime. So x is equal to x prime cosine theta minus y prime sine theta. Y is equal to x prime sine theta plus y prime cosine theta. Okay. Nicely enough, okay, these actually end up being the same values as in the last problem, but I'll show you again where these come from. So y is equal to x prime times cosine of pi over 4. Remember, we said it's easier if we use 1 over root 2, minus y prime sine of pi over 4, 1 over root 2, which we can simplify and turn into x prime minus y prime over root 2. And that's x, not y. Sorry about that. That's x. Y is equal to x prime sine of theta is 1 over root 2, plus y prime cosine of theta is also 1 over root 2, which is going to simplify to x prime plus y prime over root 2. So I'm going to jot those down so I can find them later. So x is equal to x prime minus y prime over root 2. Y is equal to x prime plus y prime over root 2. Now that I have found those, we are now going to substitute those into the original equation to find our rotated version. So we have 5x squared, so that means that we have 5 x squared is x prime minus y prime over root 2 squared. The next term was minus 2xy, so minus 2x is x prime minus y prime over root 2. Y is x prime plus y prime over root 2. Plus 5y squared would be x prime plus y prime over root 2 squared. Okay. The next part of the equation is minus 12 equals 0, so I'm just going to move that to the other side and make it equal 12, because when we deal with our conic sections, we usually have it equaling something that's not 0. So we'll just put the 12 over there and be done with it for right now. So once again, here comes the algebra. We have to square x prime minus y prime over root 2. So we'll get 5 times, so x prime squared minus 2x prime y prime plus y prime squared over 2. So this is the shortcut for foiling a binomial. Square the first term, square the last term, and the middle term is the product of the two doubled. Minus 2 times, now remember these are conjugates, so we don't have to FOIL, we just have to shortcut and do first times first, last times last. So we'd get x prime squared minus y prime squared over 2 plus 5 times, once again we're going to FOIL this, so we'll get x prime squared plus 2x prime y prime plus y prime squared over 2 equals 12. Okay. Now we need to do some more multiplying and distributing. Okay, a little bit more cleaning up. So the first thing we'll see is that these 2's here cancel, which I think we're going to want to do, but then the more I think about it, that initial instinct to just cancel these out and be done with them isn't what we want to do, because this is a 5, this is a 2, those are not going to simplify, which means the first term here and the last term here are still going to be fractions with a denominator of 2. So if we get rid of this 2, we're just going to have to get common denominators later. So instead of getting rid of it, I'm going to distribute the 2 through the equation. So I'm going to do that with everything. We get 5x prime squared minus 10x prime y prime plus 5y prime squared, and each of these are over 2, minus 2, and then we have x prime squared minus, and that's going to turn into plus because we have minus a minus, so that turns into plus 2y prime squared, and each of these are also over 2, plus 5x prime squared plus 10x prime y prime plus y prime 5y prime, plus 5y prime squared, and these are also all over 2, equals 12. I don't know about you, but I'm getting kind of tired of writing down all these fractions. After I combine like terms, or while I combine like terms, or before I combine like terms, at some point while I'm combining like terms, I'm going to multiply everything by 2. Okay, so by multiplying everything by 2, this side turns into 24, and all of these denominators go away. Like magic. Okay, now I have 5x prime squared. Okay, I'm going to try to color code these. So I have 5x prime squared here minus 2x prime squared here plus 5x prime squared here. So 5 minus 2 is 3 plus 5 gives me 8x prime squared. Now I have a negative 10x prime y prime and a positive 10x prime y prime, so they cancel. Yay. And then I have 5 plus 2 is 7, plus another 2 is 12. So plus 12y prime squared equals 24. In order to get this in the form of a conic, we're going to divide everything by 24. So 8 over 24 is going to turn into x prime squared over 3 plus y prime squared over 2 equals 1. So there is our equation. Now we can find the stuff that we need to find. Looking at this, because it's a plus in the middle, it means it's an ellipse. From here, we're going to find our vertices and covertices. So the vertices on our x prime y prime plane are, the 3 is bigger than the 2, so the vertices are in the x direction at root 3 comma 0 and negative root 3 comma 0. The covertices are along the y direction at 0 root 2 and 0 negative root 2. Okay, so this is where my vertices and covertices would be on the rotated axis. But those are not very helpful because I don't know where they are. I mean, I have an idea because I know that my axes are going to rotate, and become here and here. But on the last example, it was hard enough to estimate where 2 would be. Now we're going to try to estimate where root 3 and root 2 are. So that doesn't really work so well. Now what we have to do is we have to take these 4 points and we have to substitute all 4 of these points into x and y to find 4 new points. That's why I put these in the box, so I could find them for later. Now I've moved my equation for x and y a little bit closer to where my ordered pairs are, so it's a little bit easier to see what's going to get substituted where. So now there's just a whole lot of math that needs to be done, but none of it is overly complicated. We just have to pay attention. X equals, so the first one is root 3, 0. So root 3 minus 0 over root 2. Y would be, we have root 3 plus 0 over root 2. So this is going to turn into the point root 3 over root 2, root 3 over root 2, which we then rationalize by multiplying numerator and denominator by root 2. So we get root 6 over 2, root 6 over 2. And you're like, gee, thanks, Miss Brown, because root 6 over 2 is a whole lot easier to graph than root 3 and root 2 on a slanted axis. I know it doesn't make much sense, but we'll get there, where finding these points on the xy plane does seem to make more sense than finding them on the rotated plane. Now, the next point we're going to use is the negative root 3 comma 0. Now, if we think about it, the negative root 3 just replaces the root 3 in these two equations. So this and this just get replaced. So the only thing that's going to change is now we have negative root 6 over 2, and this one also becomes a negative root 6 over 2. Okay, so there's two of our points. These are our vertices. Then we need to find our covertices. So our covertices would be x equals, now x is 0 and y is root 2. So x equals 0 minus root 2 over root 2. Hey, look at that. That's negative 1. X is going to be negative 1. And then for y, we get 0 plus root 2 over root 2. So y equals 1. So that's one of our covertices. Okay, so we have negative 1, 1. That's a nice point to graph. Okay, Miss Brown, we're starting to believe you now. Next, we have to find our last point. So that one is the ordered pair 0, negative 2 we have to substitute in. So if we think about it, the only thing that changes are the positive and negative values here. So that means our other covertice is located at 1, negative 1. So the points we are plotting, first I'm going to do the covertices that are negative 1, 1 and 1, negative 1. So negative 1, 1 and 1, negative 1. Okay, so I've got those points. Now I have root 6 divided by root 2, which root 6 divided by root 2, you're like, Miss Brown, I have no idea what that number would be. Well, that's where our handy-dandy calculators can help us find a decimal approximation. So here's a better sketch of what it would look like. We have our vertices here at approximately 1.7, 1.7, and negative 1.7, negative 1.7, and then we have our covertices at 1, negative 1, and negative 1, 1. I've also sketched in the rotated axes here. So if we look, this was originally the x-axis, so it rotates to here, so this is the new x-axis. This was the y, so this is the new y. This is negative x, and this is negative y.